Hey everyone, thank you for joining. Today I want to talk about cost-effective big data storage in the cloud using simulated annealing. My name is Dr. Lazebnik from Datacolo, and the image on the right is how it looks like, at least when I'm trying to be serious. So just a quick addenda about what's going to happen in the next 15 minutes. So first, a quick introduction for data storage in the cloud, which the associated cost. I'm sure most of the audience is familiar with data storage in the cloud and how much it costs, but just to make sure that everybody on the same page. Afterwards, how is better to store your data with simulated annealing? This is just the algorithm, and we'll describe how we used it in this specific context and what it is. A few empirical results, and finally, if you have some time left, additional thoughts and conclusions. So without further ado, a quick introduction, storing data in the cloud. So just to make it clear, in this presentation, I'm gonna explain only for Google Cloud Platform or GCP, as most of you probably know it, for the European Union regions. It's not just a specific region, just like all the regions in the European Union. It's actually even cheaper for a specific region. The reason for this configuration is just because the client or the originated the project is from, well, UK, and he used GCP. So as you can see on the left, actually the data is from the official GCP cloud, website, is the four main configuration of data storing in GCP. The archive, code line, nearline, and standard. When standard is basically not a storing, but a service, but more like Kubernetes, live servers, and so just memory for your computational machines. So as you can see, it's a bit different. It's different because you can access it in a second and get your answer relatively fast, like minutes of seconds, milliseconds, minutes, etc. But it's really, really expensive. How much expensive? 2.5 times more expensive than the next solution, which is the nearline storing. As you can see, the nearline, code line, and archive is all really, really just storing services, because you can get it or use the data once a month, once a quarter, or once a year, and you can see a linear drop in costs. So we will mainly focus on these three, but we cannot ignore the standard storing option, just because it's actually a movement between the three types of storing, which more hot or usage specific usage of the data in the standard storage type. So a quick introduction to cost in GCP. Next thing in line, simulated annealing. So simulated annealing is a probabilistic technique for approximating global optimum function. It's actually historically based on the idea of how metals are cooling down. So as you can see on the left, we have time and have temperature. The temperature is monotonically reducing over time and decreasing over time. And the idea is you have a fitness function, the gray fitness function you see on the boxes. And the red point is the optimal solution that's going around, and we're trying to find the optimum. And as you can see in the beginning, it's really, really hot and have a lot of energy. This energy allows it to jump over the mountain on the right and finding the optimal solution on the right, as you can see on the right bottom box. So this is the general idea. It's more complicated than that, but what we can explain in 30 seconds. Next, so let's talk about storing data. So first, this is a data point. It's a good start. But a data point has a few attributes. So the first one of them is size, of course. And we will talk about gigabytes, because this is the standard costing plans are associated with gigabytes per month. It has how frequency you're using it. So you can use it once a day, or you can use it once a month or once a year, et cetera. So frequency of usage is really, really important in storage and data. This location. So in location, we're mostly talking about regions, because moving between regions, etc., will be costly and hard to manage. So it's important where they're stored. And how urgent is using the data once we need it. For example, let's talk about GDPRs as usual. So if you have a GDPR and we need to answer it, a GDPR request, and we want to answer it, we need it quite urgent, but not urgent in a second, but in hours. So if it took us a few hours to gather the data, it's fine for us. So it's hour level urgent. So it's important to understand how urgent data is. And this is actually affecting how we'll store it. So another few attributes are problematic because the presentation have a technical problem saying they don't have enough time, just 20 minutes, and therefore we don't have time to answer or present all the attributes. So let's just assume the execution and networking is framed optimal. They are not, they're actually really, really complex, and we just ignore it in the sake of time. So this is just a single data point, which is really easy to handle because if you have only one data point, you just put it in the right bin. But what happens if you have a lot of them? And each one has a unique size and frequency and the region, et cetera, et cetera. So it's starting to be more complex. So just to make it clear, the problem is as follows. We have a data set, which actually constructed by a bunch of data points. I will talk about what data points in a second, like empirically. And we have a lot of, on the other hand, we had a lot of bins. So we discussed 4 bins, standard, nearline, codeline, and archive bins, but actually there are much more than that, because each one of them has a unique configuration. You actually can have each one of them in a few regions, which can modify the cost, and you can modify the performance, et cetera, et cetera. And the idea is to put in the left side, the data set in the storage by maximizing or optimizing to objective, maximizing the performance and minimizing the cost. So this is the general idea. It's not that technical yet. So give me a second. Let's define it more specifically. So for the simulated annealing of the optimization process to happen, we will need to treat each data point, which is, for example, PDF file, image file, JSON object, log file, anything like that. We want to compute the attributes needed for the algorithm. Therefore, it will be described in much more than that. This is like the first thing we need to do just to prepare the data for the algorithm. Afterwards, we want to go to the client cloud, extracting the current storage location and types. For example, the standard nearline, codeline, archive. There are much more than that, not only that. And computed the cost plan, just a baseline. We don't really need the baseline. We just need it to show the improvement over the what happened if you don't change anything, making sure that the proposed algorithm is indeed improving and not doing harm at any point of time. And finally, we actually can further configure the process, finding the optimal solution sensitive to the plan duration. So you can have short plans, long plans, and it's in the middle. We can weigh the performance versus the cost. Just for example, let's assume we don't have any importance for the performance and we want just the cost. So basically you can put all your data points or the data set in the archive. It's really, really cheap and you don't have any problem with the performance. On the other hand, if you want just performance and don't care about cost, put everything in the standard. It's really, really expensive, but you get everything like in the same second that you need it. So, well, it's really, really performance oriented. So the truth is usually somewhere in the middle. And the client or yourself can actually play a bit with how much performance over cost on the other way around we want to configure the process. And finally, it has another constraint. Just for example, we cannot use specific regions for specific data types, or we cannot put logs in the same region as, I don't know, your JSON objects, et cetera, et cetera. Each client has a unique constraint, either from basic or technological point of view. So we need to take them into consideration. Formally, you can write down the formula for the paradigm as follows. I have a policy P. The optimal policy is one, minimizing the cost, optimizing or maximizing the performance. W1 and W2 is the way that we just talked about. Big T is the period, and P is the policy that we're looking for. So just to make it clear, cost PT is straightforward. It's basically the bins that we want to use, how much data we want to store at any point of time, and how much it costs to store each data over time. This is a multilinear function, basically easy to use, easy to solve, really, really nice. On the other hand, we have performance PT. It's a bit more complex, and I cannot provide a simple solution for it, a simple example for it, because it's mainly dependent on the client's definition. So performance can be how quick you answer a query, or performance can be how easy it is to get a really complex ML algorithm to run on the data, or gather the data, and something like that. So like it's a wide range of uses, and it will be hard to say a specific performance one. It's mainly dependent on the client's definition. So from our point of view as algorithm developers, have a few other tricks in the sleeve. So the first one, we actually tried 3 temperature functions. So the algorithm annealing, as we recall from 10 minutes ago, is based on some temperature reduction over time to get the right solution. So we plan a bit with this function to make sure the results are good. And more than that, we are actually making sure that the solution is the majority vote of the multicolor initial condition run. Pardon my French. In English, it means that we rerun the algorithm several times, each time storing the answer it provides from the different initial condition. We want to make sure that the solution or the answer that the algorithm provides is the same for most of the initial condition, making sure or making us more statistically confident about the fact that this is indeed a global or at least a really good local optimum point. Finally, we want to make sure that the solution is Lyapunov stable, or the stability or Lyapunov stability is small enough. What I mean by that is that if we have a big change in the fitness function, configuration, something like that, small changes won't produce a lot of change in the solution, making it more robust and more stable for users in the long run. So we really want to make sure that before we actually proposing the plan to the client, we want to make sure that it's stable, it's robust, and we can actually be sure we can use it over for a few months or so. That said, few use cases. So imagine yourself a British company, a small medium one, around 200 employees. It's in the field of biotechnology, not really important, but nice to say. At the beginning of the project, they had 1.2 thousand terabytes of data, and they're planning to add between 50 to 200 times of data a month. These numbers are a rough approximation of the previous 1 year history of how much they added the data and continuous growth of the company. And finally, most of the data is not urgent data. It's analyzed once or twice during the pre-process phase, and it's mainly stored for global reports afterwards for the users request, which is not really often. So it's mainly like high peak in the beginning, high peak somewhere in the future, and nothing in between. Again, should be taken into consideration while developing the fitness function. So, which drums the outcome. For 3 months plan, we actually wanted to show more, but the company changed the plan just 3 months ago. We sell the company around $60,000 just, and I want to make sure it's clear, just for storing, without networking, communications, pre-process computation costs, and so on, etc. Just storing the data, 35% of the original cost, or the estimated original cost, reducing it from 45,000 something to 29 something thousand using the proposed algorithm. It's fair to mention that the baseline cost is approximated based on historical data, while our plan is actual measurements. Okay, we cannot measure both of them because the company will sell both options just for measurements. And indeed, the following graph showing the improvement. So as you can see, the first 2 weeks actually it's a bit more expensive because you're making a lot of change for the how you store data. So moving stuff and storing them differently is a bit more expensive, but you get a break even just in 6 weeks. Afterwards, you're actually making profit and making the overall plan much more attractive. Additional thoughts. So because we don't have a Q&A session, just trying to predict what kind of question you might have and answer them in advance. So the first one is, why simulated annealing? Did you try other optimization methods? So the answer is yes, we actually tried a lot of them. It just worked the best. We have a really interesting hypothesis why it worked the best, but we don't have time for in this presentation, so we're glad to talk about in the break. Next, can it include other operation, other associated costs? The answer is yes, it does. Actually, we did it in the project itself, and it's more or less trivial to add it to the fitness function once you understand it, but not that trivial. Usually people asking, can I use it for my project? The answer is sure, of course you can. The idea is all yours, but we won't publish the code anytime soon, IP and stuff. So just to conclude, the main contribution of this presentation is sharing with you an idea on how you can treat storing data as an optimization problem. We propose an algorithm that's able to make a generic NoSQL data set and provide an optimal storage plan. The reason I'm saying NoSQL because we don't actually work in rich tables of data, but as data points, as I mentioned before. So you can treat it as like NoSQL. For example, having a lot of data points in object files of, JSON files, etc., etc. And more than that, we show a use case in which the proposed algorithm improved the baseline plan, showing that this is not just a theory and stuff, it's actually working in practice, and you can use it in your company or project. So just to wrapping it up, we're always looking for interesting research and business collaboration. This is my email. Send me an email, give me a call. Always like to hear about from other people about cool projects with a lot of interesting questions and data. And that's it. Thank you for listening.